Okay, so this is a Zoom meeting for Physics 231C of October 20th. So we're right here. So we're at the end of the third week of October, and we're working on chapter 8. That's that chapter on rotations. We've talked about lots of general principles of motion, and last week was an example, oscillations. And this week is another example, rotations. The reading quiz for chapter 8 is due at the end of today. The large problem set for chapter 8 is due Wednesday. That's Wednesday of next week. Normally we have the problem sets due on Mondays, but next week, Monday is a break day and Tuesday is a break day. So the problem set will be due on Wednesday. And the next day, Thursday, will be the second exam. So I'll say a little bit about exam 2 at the end of the Zoom meeting. But the main purpose of the Zoom meeting is to review some of the important equations for chapter 8, and then look at some example problems, which are on the homework assignment. So chapter 8 is on rotation, rotational motion. Unlike the previous chapters where we were dealing with an object moving in space, in other words, translation, where we're really only looking at the center of the object. We think of it as a particle or a sphere or just any kind of object, but we're just looking at how does the center of the object move. Here, we're looking at the rotation of the object, that is to say, how its orientation changes in time. So we'll use a different kind of coordinates. Instead of just Cartesian coordinates X, Y, and Z, which describe the position of a point, namely the center of the object, we'll use angles to describe the angular orientation of some kind of extended object. So chapter 8 is actually pretty long. It has, I guess it has 9 sections. The first section is on kinematics, where we introduce the angle theta. That's the orientation of an object which can rotate. So theta is an angle, and normally it's measured in radians. The definition of radian, the radian measure of angle, is its arc length over radius. So in other words, if there's some arc which is moving, which is, kind of an arc around some origin. So here's the origin. Then this angle is theta. The radius is the distance from the arc to the origin. Theta measured in radians is the arc length, so this length, divided by r, s over r. Now to convert from radians to degrees, you have to take the radians, divide by pi, multiply by 180. Well, that's position. And now if you think back when we studied kinematics for motion of a point, the derivative of the position, or the rate of change of the position, I should say, is the velocity. And here we'll call it angular velocity, and we'll use the Greek letter omega for angular velocity. It's the change in the angle that occurs over a time delta t divided by delta t. And this is the instantaneous velocity. If I take a small time interval delta t and I consider the ratio with the small angular change that occurs during delta t. Then finally, there's an acceleration, which is the rate of change of the velocity, and we'll call that alpha in the case of angular motion. So alpha is the rate of change of omega with respect to time. Now, just as there are kinematic equations for motion of a point with constant acceleration, there are completely analogous equations for rotation with constant angular acceleration. So omega is omega 0 plus alpha t, where omega 0 is the initial angular velocity. Alpha is the angular acceleration, which we're taking to be constant here. So this is only relevant or only correct in the case of constant angular acceleration. Theta is theta 0 plus omega 0 t plus a half alpha t squared. And there's a relation between omega squared, the square of the velocity, and the change in the coordinate. So omega squared is omega 0 squared plus 2 alpha delta theta. And you'll recognize that these three equations you'll recognize from chapter 2, where we were talking about motion of a point in space. We had the very same kind of equations if the acceleration of the point was constant. So a lot of the things that we did in chapter 2 for motion along a line apply also to rotations. Now, there's a relation between tangential motion on a circle. So let's draw a little picture here. Suppose we had a circle of a certain radius. So let's call it R. And we consider the angular velocity of a point on the circle going around the origin, which is the center of the circle. Then for that point on the circle, there's a tangential velocity, which is the direction, which is the velocity vector, not angular velocity, but linear velocity, tangent to the circle. And that's r times the angular velocity. And there's a tangential acceleration, which is r times alpha. Now, there's also a radial acceleration, which we studied before, that's minus v squared over r, or minus r omega squared. That's towards the center of the circle. So that's the centripetal acceleration. Then there's a section on kinetic energy. Well, we know the kinetic energy is 1/2 mvi squared, or 1/2 mv squared for a point moving in space. Now, suppose we have an object. Suppose we had an object moving around. So here's some kind of an object. Every point, which is rotating around an axle. So here's maybe the axle. Every point on the object is moving on a circle around this axle. So it has a linear velocity. And so the total kinetic energy of the whole system will be the sum 1/2 mivi squared, the sum of all the kinetic energies of all the different points within the object. And vi is r omega. So I could write this as 1/2 m r squared omega squared. And every point in the object has the same angular velocity. So I can factor out the angular velocity, that's omega, and then the constant that's left, I can also factor out 1/2. The constant that's left, I can call the moment of inertia, I. Or in the table, I think they call it the rotational inertia. But it's usually denoted by the letter I for moment of inertia, and you see it's just the sum miri squared. Now, if this is some collection of points, well, then you just have to do this sum for the different points. But if this is, I don't know, some kind of an object with a shape, then you'll have to sum up over all the different points within that shape. And in table 8.4, that's page 167, it gives the results for the moment of inertia for various shapes. So for example, if the rotating object is a rod and the axle is in the middle of the rod, so the axle is at the center, then the moment of inertia, this I, is 1/12 ml squared, where L is the length of the rod. Or for a cylinder with an axle, or a disc with an axle through the center perpendicular to the disc, the moment of inertia is 1/2 mr squared, where r is the radius of the disc. Or for a sphere, the moment of inertia is 2 divided by 5 mr squared. To calculate these moments of inertia requires calculus. We don't use calculus in this course, but we will use these formulas for different kinds of shapes. And so the homework, you're going to need some of these moments of inertia, which is in table 8.4. All right, well, that describes the kinematics and energy. Now there's a section on rolling bodies. A rolling body is something that's both translating in space, the center is moving in space, so that's translation, and rotating around an axle. If it's a wheel, let's say, it's just rotating around the axle that the wheel is mounted to. So the total kinetic energy would be 1/2 mv squared, just like if it was a point, plus 1/2 I omega squared, just like if it was a rotor, where again, you would use the moment of inertia appropriate for the shape of the rolling body. And if there's a rolling body, there's a relation between the motion of the center and the velocity of the center and the angular velocity as it's rolling, as it's turning. V of the center of the rolling object, that's the linear velocity of the center of the object, is omega times r. R is the radius of the rolling object, and omega is its angular velocity. There's also a generalization of force, which for rotational dynamics is torque. So torque is sort of like length times force, only it's not quite that simple. It's distance times force times the sine of the angle between the vector from the center or from the origin to the point where the force is acting, and the force vector. So, r is the distance from the center to the point vector, to the point where the force is acting. But that has a direction as well. And F is a force, so that's a vector. So the torque is RF sine theta. And you really have to look at the pictures carefully to understand in this equation, what angle are you talking about? It's the angle between a displacement and a force vector, a displacement vector and a force vector. So these are just equations. For each equation, there's a picture. You should be able to draw the pictures. When you're reading the chapter, you should be taking notes. And, in your notebook, write down the equation and draw a picture which shows what the various variables are. And you're going to need those kind of notes for the exam, which is coming up next week. All right, well, those are 6 sections. Then there are 3 more sections. There's a section on mechanical equilibrium. An object, an extended object, is in equilibrium if the net force is 0 and the net torque is 0. So in other words, the net force vector, the sum of all the force vectors that are acting on the object, must be 0 to be in equilibrium. Otherwise, it would accelerate by Newton's second law. So this is only for equilibrium. And then the torque around any axle within the object, the net torque around that axle must also be 0. Otherwise, it'll have an angular acceleration. And so, sort of force we're familiar with from previous chapters, torque is R cross F, like displacement multiplied by force, but as vectors. And if you add up all the torques around some particular axle, usually in the problem it's clear where you should put the axle, the net torque has to be 0 if for equilibrium. Equilibrium means it's not going to move. It's just going to sit there. It's just going to stay there. So the net force has to be 0. The net torque has to be 0. Then section 8 defines angular momentum. Remember, in the case of linear motion along a line, we had a velocity vector, and we also had a momentum vector. Momentum was chapter 6. That was mass multiplied by velocity. Well, in the case of rotational motion, it's moment of inertia multiplied by angular velocity. So I is sort of like the mass term. It's the inertia term. And omega is like the velocity term, only it's the angular velocity. And then the rate of change of the angular momentum is the torque, the net torque about whatever axle is present. Just like the analogous equation for linear motion, the force is equal to the rate of change of the momentum. So All of these rotational equations are analogous to equations that we saw before for motion of a center, or of a particle, or of a sphere or something. But now we're not talking about the motion of the center in space. We're not talking about that translation. We're talking about the rotation, or the change of orientation of some kind of extended object. Well, anyway, this is how angular momentum comes in. It's very analogous to linear momentum. Remember, linear momentum back in chapter 6 was P. That goes along with m times velocity. And the rate of change of P was the force. Well, you just substitute the various quantities into their angular analogs. Then the most complicated, or the most difficult to understand, is that these various quantities are in fact vectors. So the rotation velocity, we call it omega, it's actually a vector. Because it's a rotation about some axle. Well, the vector is in the direction of the axle. So the direction of the angular velocity is called n hat. It's the direction of the axis about which the object is rotating. And similarly, momentum is mass times velocity. Well, momentum is mass times velocity. In the case of linear motion, mass is just the mass, a scalar. Momentum and velocity are vectors. Well, same is true for a rotational motion. The angular velocity is the moment of inertia times the angular velocity. And alpha is, since omega has a vector, and alpha is the rate of change of that vector, alpha is a vector. It's the rate of change of the velocity vector, the angular velocity vector. And torque is a vector. Torque is I times alpha. I is a scalar, but alpha is a vector. So torque is a vector. So torque has a direction. Torque has a direction. What direction is it? Well, that's given by the right-hand rule. It's the direction perpendicular to the plane spanned by R and F. So you really got to look at the pictures in this chapter to see all the directionality. That's section 9, and that's kind of the most advanced part of chapter 8. Okay, so that's kind of a review of the equations. When you read the chapter, write down the equations in your notebook, take notes, and remember to include those notes in your equation sheet for exam 2 next week. Now, the rest of today will be to look at a few examples. So these are examples which are taken from the homework assignment, which is due next Wednesday. Here's a problem from the chapter. It's problem 47, a pulley and a weight. So you have a disc and you have a little block which has a mass m. And this disc has a radius r, and this block can go down from some initial height 1 meter. So we always start by drawing a picture and labeling it. Well, here's the picture. There's gravity pulling the mass down. There's also a string attached to the top of the mass and attached to the pulley, or attached to the disc. So as the block goes down, the string causes the disc to rotate. So there'll be a torque. And T here stands for the tension. And in the problem, the first question is, what's the angular acceleration Now, you're given the angular velocity, you're giving the acceleration of the block. And so as the block moves down, that changes the angle or the orientation of the disk. In fact, if there's a change in the, let's call the coordinate y for the vertical coordinate, if y changes by some amount, there's a change in the angle, the orientation of the disk. The change in the angle is the change in y divided by r, where r is the radius of the disk. Now that relates the angle of the disk and the height of the block. Now, what about the angular velocity? Well, angular velocity is delta theta over delta t. So that's delta y over delta t. That's the velocity divided by r. And what about the angular velocity? Well, the angular velocity is the rate of change of omega, delta omega over delta t. Well, that'll be delta v over delta t divided by r. See, r doesn't change with time. R is a constant. It's just the radius of this disk. And delta v over delta t is the acceleration. It's the acceleration of the end of the string, or it's the acceleration of the block. So alpha is a over r. So the first question is, what's alpha? Given this information about the geometry of the system, well, it's a divided by r. So it's 4 meters per second squared divided by 2.5 centimeters. 4 over 2.5 would be 16 times actually 10, because this is centimeters. So the angular acceleration is 160 radians per second squared. You know, what's the unit? It's meters per second squared divided by meters. So what's meters divided by meters? Well, if I think here of meters divided by meters, that's radians. So alpha is 160 radians per second squared. And now what's omega? The other question is, what's omega when the weight hits the floor? Well, we have here a problem with constant acceleration. If you think back to earlier in the chapter, when there's constant acceleration, you can say delta v squared is 2a delta y. Now, v starts at 0, so delta v squared is the same as v squared. Is 2a delta y. So omega is v over r, so omega squared is v squared over r. So I have 2a delta y over r squared. 2a is given as 4 meters per second squared, r is 1 meter. That's that 1 meter. And the radius is 2.5 centimeters squared, so it's roughly 113 radians per second. To take the square root of this. This is omega squared, so you have to take the square root of this. And you'll have a unit radians per second. Here you have 1 over second squared. You actually have meters squared over meters squared. That's radians squared divided by second squared. When you take the square root, you'll have radians per second. That's the problem. Now, you could also be asked, what's the moment of inertia of the disk? That's not asking the question, but you could be asked, what's the moment of inertia of the disk? There you would analyze the various forces. So this is the equation for the force times mass times acceleration is the force on the block. Well, that'll be mg down and T up. T is the tension. And what's the torque on the disk? Well, T is pulling it down. So the torque is just the distance, that is the radius, times the time, times the tension, and torque is moment of inertia times alpha. So we can solve for the moment of inertia. R is, R times, let's put in here T, mg minus ma, divided by alpha is a over r. Clean it up a little bit, use some algebra. It's mr squared g over a minus 1. You can't determine the moment of inertia here actually without knowing what's the mass. But if we said the mass is 1 kilogram or something, then that'd be the mass of the block. Then we would have all the necessary things to calculate the moment of inertia of the disk. Now, as you see, G is 9.81, A is 4, 9.81 over 4 minus 1, that's a number greater than 0. You see, the acceleration has to be less than the acceleration due to gravity because the tension in the string is pulling it up. Or in terms of energy, the acceleration is less than the acceleration due to gravity because some of the work has to go into rotating the disk. So A is 4 and not 9.81. This block does not fall with the full acceleration due to gravity because it's attached to the disk. But anyway, these are the kind of equations you need to know in order to analyze the rotational motion, which is part of the motion in this system. Here's a problem from the, again, there are problems like this. I don't know if exactly this problem is in the homework assignment, but there are problems like this. You have a sphere rolling down a ramp, and you're given information about the distance down the ramp. Then when it reaches the bottom of the ramp, it rolls along the floor. The angle of the ramp is given as 15 degrees. This height would be, well, if I look at this right triangle, this height would be the distance times the sine of the angle, because this side of the right triangle is the opposite to the angle. Now, to analyze the motion of the rolling ball, the rolling sphere, the easy way is to use conservation of energy. It starts out with gravitational potential energy, mgh. At the bottom of the ramp, it no longer has any gravitational potential energy because this is ground level. Now all of the energy, but energy is conserved. So there's the same amount of energy. It's just not in the form of potential energy. Now there'll be kinetic energy, 1/2 mv squared plus 1/2 I omega squared, because this is a rolling object. Now, for the rolling sphere, V is R omega, and I is 2 divided by 5 mr squared for a sphere. So if I combine these, this is 1/2 mv squared. This will be 1/2 of 2 over 5 mv squared. So I have a common factor of mv squared, but I have a half plus 1 over 5. So that's 7 over 10. So the kinetic energy as it leaves the ramp is not 1/2 mv squared, because that doesn't take into account the rotational energy. It's 7 divided by 10 mv squared. A half plus a fifth. Now we're going to need to know the velocity, so we can just solve this equation for v squared. It's 10 over 7 gh, and h is d1 sine theta. The velocity, we would take the square root. So you take the square root of this to get the velocity, or the speed at the bottom. Now, of course, on the floor, the speed will be constant because there's no addition of energy. So the distance on the floor will just be that speed times the time that it's on the floor. So the time that it's on the floor on the horizontal part is just the distance that's given in the problem divided by v, this final velocity. It doesn't ask what's the acceleration as it rolls. Oh, but you want to find the time that it takes to roll down. So to figure out the time that it takes to roll down, well, time is the initial speed is 0, so the final speed divided by the acceleration. You know, acceleration times time is speed. So that tells you what the acceleration is, because this tells you what the final velocity is. So the conservation of energy will tell you the final velocity, but you also need to know the time. So for that, you need to know something about the acceleration. And then we also have this equation for constant acceleration. So this tells me the acceleration. It's v squared over 2d. So I have to kind of go around in circles. Here I calculate v. Here I calculate a. Here I calculate the time. That's the time to roll down the ramp. Then there's the time to go across the floor. And the answer to the, it says calculate the total travel time. That'll be T1 plus T2. Here's a problem which involves rotation, but really it involves static equilibrium. So it doesn't really involve rotation. Nothing's rotating, but there's torque. And there could be rotation because you have an extended body. So this is from section 7. To have equilibrium of an extended object, the torque, the net torque has to be 0 about some point in the object, some useful point in the object to calculate the torque. You see if the, where was it, the ladder. You see if the ladder, if there were no friction with the floor, the ladder would just slide out this way, slide down this way, and then you would have rotation. So if there weren't any friction, the ladder would rotate and it would fall down. What's keeping the ladder up? Gravity is pulling the ladder down. What's keeping it up? Well, there's a force where the bottom of the ladder, the base of the ladder, hits the ground. And so there's an upward force on that point. There's also a frictional force at that point. There's also a contact force between the top of the ladder and the wall, and we'll say that the friction here is negligible. So why doesn't it fall down? Well, it's really the presence of the frictional force down here, plus the contact force of the ground. Contact force of the ground says the bottom of the ladder can't go down into the ground. The frictional force says it can't go sliding off this way. So there's some contact force with the ground. Now, static equilibrium means the torque, in this case, the torque about any point is 0. Because if the torque were not 0, then it would accelerate, it would be an angular acceleration. It would accelerate in the direction of rotation. So we can take any point on the ladder to calculate the torque, but the easy one is this point. If we use this point as the axis of rotation about which to calculate the torque, there is actually no rotation because it's equilibrium, but the axis about which to calculate the torque, you see, torque is force times distance, and the distance, this force is at distance 0 from this axis. So I don't need to know this force if I use this point as the axis. I could put the axis for calculating the torque anywhere on the ladder, but it'll be easiest if I use this point. Now let's write down the equations for static equilibrium. The net force must be 0, so F sine theta, that's an upward force, minus mg, that's a downward force, must be 0. And F cosine theta, that's a horizontal force, minus the force of contact with the wall, Fw for wall, that has to be 0. And the net torque about this point has to be 0. So let's calculate the torque. Well, here's a force which creates a torque in the counterclockwise direction about this point. The torque will be the force times the distance. It's actually the perpendicular distance. Now, the perpendicular distance will be the sine of theta, L sine theta. So F L sine theta is the torque about this point due to this force, which is pushing the ladder away from the wall at the top of the ladder. So, you know, torque is usually a force times a length times the sine of an angle. Here we see it's the force, the length is L, and the sine of the angle, what angle is it? Well, it's this angle. So it's a little tricky to figure out what the angle is. It's really the perpendicular distance from the axis to the line of force. The perpendicular distance, this distance would be the sine of this angle, L sine theta. Now, gravity is also producing a torque. There's a downward force, and gravity acts equally on each point on the ladder. We're taking the ladder to be kind of a uniform, like a uniform plank. So the force of gravity can always be rewritten as if all the mass were at the center of mass of the object. So the mass is m. The force is mg, directed downward. The position of the force can be taken to be the center of mass of the ladder, because the forces at all the points along the ladder are equal. So if I calculate the total force, or rather the total torque, it's as if all the force were acting at the center. So that's the distance L over 2. So I'll have the force, that's mg, the distance L over 2, and then the sine of the angle. Well, what angle? Well, it's actually this angle. It's actually this angle up here, which is relevant in the case of the gravitational force. This problem of the leaning ladder is explained in the textbook. So read the example carefully of the example of the leaning ladder, and then you'll see that, well, this produces a counterclockwise torque. So let's take that as positive. Gravity produces a clockwise torque, so we'll take that as negative. The force is mg. The distance can be taken as the distance to the center of the ladder. And then you have to have the sine of some angle, but it's not this angle, it's this angle. And the sine of this angle is the cosine of this angle, because this is a right triangle. So I have this equation for the net torque to be 0. Sine of 90 minus theta is the same as the cosine of theta. Think back to high school trigonometry. All right, so now we have 3 equations for 3 unknowns. So it's like any physics problem. We draw a picture and label it. We write down the equations, and now we have to apply algebra. In this case, we get 3 equations with 3 unknowns, and you have to apply algebra. So, you know, f in the x direction, f cosine of this phi is got to be fw. F in the y direction, that's this direction, that's f sine phi. That's got to be mg. That's this equation. And then if I solve this equation for fw, move this to the other side of the equation, divide by L sine theta, fw is mg 1 over 2, the L's cancel, cosine theta over sine theta is cotangent of theta. So you see I have 3 equations. You know, this equation is, I guess, this one. This equation is this one. And this equation is this one. And what I'm trying to calculate, I'm not sure what I'm trying to calculate. I guess you're trying to calculate the force. I think you're trying to calculate, maybe you're trying to calculate this force. I'm not sure. But if I look at this, this would be the formula for this force, where everything else is given in the problem. Let's see, I'm kind of running out of time here. Problem number 894 has to do with a particle moving on a circle. The Bohr model of the atom, which you may have studied if you've taken chemistry, has an electron circling around a proton. So this is like a hydrogen atom. A hydrogen atom has a nucleus, which is a proton, and an electron that circles around the hydrogen atom. That's the Bohr model. The angular momentum is mRV. V and R are at 90 degrees, so R cross V is just R times V. In general, it's R times V times the sine of the angle. That's the angle between R and V. But R and V here are perpendicular because this moves in a circle. It's circular motion. So the sine of 90 degrees is 1. So the angular momentum is mRV. And it says calculate the angular momentum. Given this speed, so this is the speed, and given this radius, that's the speed and radius that comes out of the Bohr model of the atom. So it's really just a question of plugging into this equation for angular momentum to calculate the angular momentum. What's interesting is that that is equal to Planck's constant h divided by 2 pi. That's in fact how Bohr first came up with this model. He said, well, the angular momentum is quantized in units of h over 2 pi, where h is Planck's constant. Now, you know, you need to know the mass of an electron. We can look that up on Google. You have to know the speed. Well, that's given in the problem. You have to know the size of the orbit. Well, that's given in the problem. So you just multiply these together. As usual, we have a number with a unit. the unit will be kilogram meters per second times meters. So it'll be kilogram, I guess I got this wrong. It'll be kilogram meters squared divided by seconds. Kilogram meters per second times meters. Kilogram meters squared per second. And it's a very tiny number. That's the Planck's constant. Now, this is just a rough estimate, but calculate it accurately using your calculator. And then there's part B of the problem is compare that. Compare that to Planck's constant, which is determined from a theory of photons. The Bohr model describes atoms. Planck's theory, in which he introduced Planck's constant, has to do with radiation. Or as Einstein explained it, photons. Well, it's the same number. This was the beginnings of quantum theory at the early years of the 20th century. Let's see, do I have any more problems? Yeah, here's one more problem. I'm kind of running out of time. The polar ice caps problem. Well, okay, I don't think I'll go over this. To do this problem, you just say, first of all, angular momentum is conserved, and angular momentum is I omega. So I1 omega 1 is I2 omega 2. I1 is the moment of inertia before the ice caps melt. I2 is the moment of inertia after the ice cubes melt. Well, there'll be a slight change in the angular velocity. Now, the period is revolution, or no, it's the period of rotation. This is rotation of the Earth, not revolution, but rotation of the Earth. The period is 1 day. The Earth turns all the way around, one complete rotation in 1 day. That's 2 pi radians divided by the velocity. So T is 2 pi radians divided by omega. That'll be radians per second. So the unit here is radians divided by radians per second. The unit here is going to be seconds. How many seconds does it take for the Earth to turn around once? Well, it's 1 day. So you see the third step is to look at the effect on the length of the day. Well, the length of the day will now be T1 times the ratio I2 over I1, which it tells you is 1.003, 0.3%. So the change in the period will be T1, T2 minus T1. T1 times 1.003 minus T1 will be 0.003 times 1 day. 24 hours times 60 minutes per hour will give it to you in minutes. All right. Now, before I quit, you may be wondering about the exam. This is completely wrong. No. The exam is Thursday, October, I guess it's the 26th. Let's just make sure. Yeah, the exam is October 26th. That's a Thursday. So the problems on rotation are due Wednesday. The next day is exam 2. So you need to do some things to prepare for exam 2. You already did exam 1, exam 2 will have the same form, so you know what you need to prepare. You need to prepare an equation sheet. A help sheet that you can refer to during the exam. During the exam, you're allowed to have one sheet of information, any kind of information you want, but probably most of the information you'll write on that are equations, because you're going to have to use equations to do the problems. So make an equation sheet. It should be one page, front and back, handwritten. You can also use the equation sheet that you used on the first exam in case you need to refer back to something that was on the first exam, because it's a cumulative process. Each new chapter relies on some things from old chapters. So you can use a new equation sheet for these four chapters, 5, 6, 7, 8. And the questions will be from these four chapters, 5, 6, 7, 8. So there'll be questions about work, energy, momentum, collisions, oscillations, and this most recent chapter, rotations. You need to have equations from all those chapters. One way to make sure you've got all the right equations is to check the equations on the summary page at the end of each chapter. At the end of each chapter, there's about 1 page or possibly 2 pages of information about the chapter, including equations, pictures, diagrams, and so on. Make sure that that information is either in your mind or on your help sheet. There's also a practice exam on Lon Kappa. So if you want to get an idea what kind of problems could I ask or could we ask, look at the practice exam to see what kind of problems there are. There'll be problems about work and energy, conservation of energy, using energy to calculate velocities and so on, momentum, collisions, oscillations. Rotations is a big chapter. So there could be problems involving static equilibrium, like the leaning ladder, problems involving the calculation of torque, or problems involving rotating acceleration. Acceleration also depends on torque, because angular acceleration is torque. I think in this book, torque is denoted by the Greek letter tau, divided by the inertia factor, which is the moment of inertia, I, about the axis where the rotation is going to occur. So be sure that you understand torque, because that applies to problems in static equilibrium and also to problems of rotational acceleration. And that, you've got to sort of look at the pictures in the textbook to make sure you really understand what torque is. Well, you'll have a bunch of problems to calculate torque. So I'm now going to end the recording.